Okay, I want to talk, a lot of the things I want to say here, gee, Leo, you already gave some of the examples I'm going to give, and you did too, Charlie, so you're going to see a couple of the examples again, and I apologize, but there's a couple of people that weren't here yesterday, so I can get away with that. All right, what I want to do is I want to talk about the source of all those problems and paradoxes in social choice. What I'm going to be telling you is forget all those issues about transitivity. It's just a special case. Forget all of these other things. That everything that I'm going to be discussing is far, far more general. It crops up almost everywhere, is what I'm going to be showing you about the difficulties. And in fact, I'll give you the answer right away. The source, what's the answer? The answer is lost information. That's simple. It's just lost information. You have the information, you have the information, you have the information. But the rules, the aggregation rules, and by the way, forget aggregation, that's just a special case too. The aggregation rules that we have for voting, they don't have that information. And so they have to deal with parts of it. And in fact, the rules we need can lose needed information. As I will indicate, this is going to be the cause of all of the paradoxes. It's going to be the source of Arrow's impossibility theorem, Sen's impossibility theorem, all of them. And in fact, it goes way beyond Arrow and Sen. So it includes, I will show you some problems from physics that it includes. And I got interested in extending some of these things right here by NSF Engineering when they asked me to look at some of the issues in nanotechnology. And I'll show you how this Arrow's theorem and that fits in here, or indicate anyway. And the next step, of course, what does this mean about the law? And that's one of the reasons for this conference, this workshop. Now, let me give you a simple example about lost information. Michael Drake is the president or chancellor of the university here. And what he's going to do is he's going to announce tomorrow that from now on we rank our students strictly according to the number of A's they receive. Nothing else. What do you think of that? Okay, right away you can see some flaws in that, because what happens is a person who gets B's across the board compared to the student who gets an A in gym and F's across the board, a gym person is going to be higher ranked. And what we have is an obvious example of lost information. Michael Drake's example, and he's not going to do this, honest. Michael Drake's example that I have right here is really the plurality vote. You only vote for your A candidate. You don't vote for your B, C, D candidates. And once that's the case, you begin to realize how to create any kind of example that you want with the lost information, exploiting it. Right here, Ann wins, there's 100 voters, Ann wins with 51, Barb gets 49, and the other two get 0. Hey, Ann is the Condorcet winner, Ann is the plurality winner, Ann should win. Let's see, Ann right here, what does she have? She has 51, Ann, Barb, Connie, Deanna is what they have. 49 have, look, everybody has Barb either first or second. And that's exactly the school ranking problem that I gave you earlier. Lost information. If you have something that would take into account second place candidates or third place candidates or something like that, Anne, who is the questionable winner here, would not win. And so that's some of the things which we have on here. It's lost information. Now, in fact, about 20 years ago, I was in correspondence with an economist at NYU, and he was trying to analyze the most valuable player ranking method that they had, for baseball. And I was still in Chicago, and I said that I wonder if we could create a method so that we could get someone from the Chicago Cubs to be the most valuable player. And he says, impossible. Chicago Cubs, impossible. So I created a theory type there. I went through and found it. And here's one of the type of examples I have. I mean, there's all kinds of them, but for 10 candidates, it's not at all difficult to create a profile with, maybe about 40, 50 people. Nobody changes their mind. Everybody keeps their same preference ranking. All we're going to do is, just like Charlie talked about yesterday, changing the rules. I'm going to change the way we tally the ballots. That's all I'm going to do. This one I might give 10 points to my first place candidate, 9 points to my second and third, whatever, different rules. And by doing that, we're going to get over 3 million different election rankings. No strategic voting or anything else, over 3 million different election rankings. When we go up to 11, oh God, it gets really horrible. And you start getting very, very large. So the point of this right here, of course, it's that, boy, we have serious, serious difficulties with aggregation type methods. And everything I say here about aggregation type methods for voting, they extend to non-parametric statistics in a large number of other areas. In other words, view voting, view social choice, view these as special cases of more general phenomena. Now, you might say, well, that's not too hard to expect because after all, we know from Arrow's theorem, don't we? We know from Arrow's theorem that once there are 3 or more alternatives, no voting rule is fair. And I think everybody here accepts that, Arrow's theorem. So let's go through and analyze that and see what it is. I mean, what we have, of course, is a question of complexity. Arrow's theorem says this is a very, very complex situation. So if we run into an issue of complexity, now I put on my hat coming from engineering and from this physical sciences, that maybe we should try the reductionist approach. We all know the reductionist approach. If we have a highly complex problem, what we do is we divide it into tractable parts. Then we study each part, get an answer, and then what we do is we put the answers together for a solution of the whole. Okay? Everybody knows this. This is a standard way of, divide the problem into easier parts, solve the parts, put them together, and then you get the answer. So let's try this with voting theory. Now the voters, we know what the inputs are. This is not anything for construction. The voters have this. They have complete transitive preferences. And we know what we want to have. What we want is a complete transitive outcome. In other words, we've been talking about cycles and other things. Let's just throw this in. You can throw in other conditions, you still get problems. All right, that's what our inputs, that's our output, and now I have to find a voting procedure. So I guess what I'm going to do is divide it into pairs. In other words, I'm going to find the A-B ranking. I'm going to find the BC ranking, and I'm going to find the AC ranking separately. How am I going to find them? I don't care. It's up to you. We'll just find some brilliant people to figure out how to do it. Okay? And then what are we going to do? Well, I want to avoid silly answers. A silly answer is where A is always better than B, no matter what the inputs are. So what I'm going to do is I'm going to say that no. I'm going to require that each pair, that there are situations where I can have A is better than B or B is better than C, or if you would prefer, maybe A and B are indifferent. But I want to have different outcomes. I'm not imposing anything other than that. And then the next question is, of course, I want to have the output that reflects the input of more than one person. Okay, no problem here. This is pretty straightforward. And of course, the answer is you put the answers together to get a societal ranking, and I don't care how these are done. And the answer is it's impossible to do. You cannot always do this. So what does this say? What is this? Why is it impossible? Because this is Arrow's theorem. This is just Arrow's theorem right here. It's a different version of Arrow's theorem than what you've seen, but it's Arrow's theorem. Because right here is the independence of irrelevant alternatives. Don't view it as something special. Really all it is the reductionist philosophy. That's all it is. It's saying we're going to solve this complex problem by looking at this pair first, this pair next, and this pair next. How you do it, I don't care. Now, in Arrow's theorem, we usually say that you have the Pareto condition. You don't need the Pareto condition. You just need something that's not constant, that's all. I don't care what it is. And this one right here is that more than one, this is the non-dictatorial condition. So really, this is the only condition. This is the only condition right here. This is the only condition, which is the reductionist philosophy. that we're going to find this problem by breaking it into pairs, finding the answers for the pairs, and putting the answers together. And the rest of the conditions are nothing more than to say, well, I don't want silly stuff. You can rewrite that in almost any way you want. And so what we have then is that Arrow's theorem does not say that no voting rule is fair at all. It has nothing to do with that, even though we've been saying that for a day and a half now. But it isn't. Really, all Arrow's theorem says is that the reductionist approach of paired comparison is not going to work. That's all it says. That the reductionist approach of trying to do something by pairs, by paired comparisons, is going to give you difficulties. Nothing more than that. Okay? Very radically different than what we normally think of it. Lost information? Well, the lost information is that we are separating. When I use the reductionist philosophy, I'm separating what's going on here, what's going on here, and what's going on here. I'm separating the connections that we want it to have. The rule doesn't know how to put them back together again. An example that my daughter uses is she says that suppose the information you got is the following, and you have to put it together to tell you what the sentence meant. That man, that's one part that you put together, his wife, the apple, smiled at, and took a bite out of. That man smiled at the apple and took a bite out of his wife. Perfectly legitimate type thing of taking from the parts, because the answers for the parts, things like that, are separated, and nothing wrong with that. And that really is what captures from the reductionist philosophy of separating the connecting parts among them. All right? Now, lost information, it's how the parts interact. Because once we do this, through the independence condition, which is just a reductionist philosophy, we are severing the connections between how the parts interact with each other. You can show that mathematically so many different ways. All right, so what's the general result? Well, really to start, I'm going to show you that Arrow's theorem is just a tip of a very, very big iceberg. Okay, and where did this come from? This came from NSF Engineering. They called me about a decade ago and said, we're having troubles in nanotechnology. We want you to help. I said, I can't spell nanotechnology. How am I going to help? They said, we would like you to do so. And I said, no, I can't do it. We'll give you some money. And I said, no. But why are you? Well, we think that you have the insight. And I said, okay, but I want the money. So what I did is I worked on it, and I came up with the following result, which includes Arrow's theorem as a special case. The result is that it's a whole parts problem, isn't it? The reductionist problem is a whole part problem. We got the whole, we're breaking it up into the parts, and we're trying to see what we're doing it. And so how the parts, if I'm looking at a situation where how the parts must be constructed, what is the kind of constraint you want to impose on it, how they must be constructed for a consistent whole, whenever that situation crops up, and I'm going to give you a couple of examples in a second, whenever that situation arises, expect the reductionist approach will not always work. Okay? Let me give you an example. The reason is that the reductionist approach puts you into the silo effect, where each of the parts, just like I showed you, with my daughter's example about the guy biting his wife, that what happens is you got this separate information, and you're severing the connections between what they are. And Leo, some of the examples you gave today had exactly that effect, didn't they? Because you're separating what's going on between one and another. And that's why we were getting the type of cycles. Remember him? Bernie Madoff? Well, what happens is, it turns out that the SAC and others knew he was a criminal long in advance. But what the SAC has is silos. And each division knew that he was indeed doing something wrong. So each division, as we found out after the fact, worked and worked and worked and they couldn't find what was wrong with them. They looked at that. That's the reductionist philosophy. They were looking at their silo, and the silos didn't talk to each other. It wasn't until the silos started talking to each other that indeed we started getting connection. And that's also getting you now to the connection of how do you get around some of the problems that we've been discussing. How do you create connections between these parts that are severed? We don't think of them as severed. But the point is that the approach that we're using does sever them. And that's it. Here's another example. Universities, the pursuit of knowledge. We do this through different departments. Or maybe in a department between micro and macro. Cherish the thought, yeah. And do we really have communications? Or no, we all know the problems that crop up there. Here's another one. Here's one. Because notice what my theorem says. It says, essentially, there's some conditions, but you can fill in the conditions. They're pretty straightforward. It says that if there are constraints about how the parts must be pieced together to get a consistent whole, then expect that the reductionist approach will not always work. That's what the theorem says. When I got that theorem, I said, oh my gosh, this is covering very few constraints on it. Well, my early life, before I discovered social choice and economics, was in mathematical astronomy, where I was working on issues like the evolution of the universe and things like this. And what I did is I said, well, maybe there's an example in astrophysics. And in fact, there is. In a galaxy, the consistency condition is given by a guy by the name of Newton. The consistency condition is that when we compute the mass of a galaxy, you know how much a galaxy is at various radii, and then that has to be consistent with the rotational velocity. Now think of it in the following way. You've all done this. You had a weight on the end of the spring and you spun it. And you know the following theorem. The following theorem is a weak string plus a rapid twist means a broken window. Okay. And what is the twist? The strength of the string? The strength of the string is given by the amount of mass. And so what they were doing is they made some assumptions. They actually used the reductionist approach, put them into separate silos. This silo, they computed the amount of mass, and then they used observations to find the rotational velocities by Vera Rubin. And they said, whoa, when we put in the answers inside there, we only know about 4% of the total mass of the galaxy, of the universe. 96% is unaccounted for. Okay? So here's an example of where the silo effect, and I'll come back to this in a few seconds. Here we go. Let's use the reductionist philosophy here. To do the reductionist philosophy here, let's first make that face all red. After we make that face all red, then let's make the other face all white. Then let's make the other face all blue. And you know the answer already. Impossibility. And the impossibility is all I'm capturing with this theorem. That's all I am capturing with this theorem. It's that there are connections between them. See, is when there are connections between how they're put together. And so the Rubik cube is a very special case of Arrow's theorem, if you will. If you're going to try to do Arrow's theorem, solve for AB first, solve for BC first, what you're doing is you are solving, trying to make this face red, this one blue, etc. That's why Arrow's theorem crops up. It's because there's interconnectivity. And in fact, the mathematics is not that far removed. Because to find how to solve this problem right here, you use something called symmetry groups. And that's precisely what you use to explain Arrow's theorem, as we'll see in all these paradoxes, as we'll see in a few seconds. Any questions up to now? Okay, then, now actually, while it illustrates the problem, it's also part of the solution. Because it says that when we try to divide things into parts, we have to see, when we're finding an answer for this part, we have to see how it works with this part, how the parts interconnect. That's the only way you're going to get a reasonable solution. Law anywhere. And interacting parts, and indeed, that's precisely what I started to do. is I've been looking at this issue right here, and some of the people that are from UCI are aware of my activities in that direction, where what I've been doing is showing that the approach they use to find the total mass of a galaxy is totally wrong, and creating a new way to find ways by talking about interacting parts to get a different way to compute mass, etc. But where does it come from? It really comes from understanding how to use Arrow's theorem to satisfy the problem in engineering, to look at it right here. Okay. Now, a lot of people have their own business, and I do too. Consulting. For a price, I will come to your organization before your next election. What happens is you tell me who you want to win. I'm an outgoing guy. I'll go and talk to everybody. And then I will design a fair election rule, and all candidates will be included. And you know what the answer is going to be. Your candidate will win. Now, actually, this can be done in all sorts of ways, but let's start off with something simple with a department of 30 people where I have 10 of them preferring Ann to Barb to Connie to Deanna. Oh, poor Fred. Nobody likes Fred. In fact, the next 5, there's poor Fred again. And the next 10, rather, there's poor Fred again. And so, of course, you're going to ask me, can you elect poor Fred? And the answer is sure, no problem whatsoever. Even though everyone prefers Connie to Deanna to Elaine to Fred, electing Fred, piece of cake. Actually, there's several ways I can do this. But I'm going, since we're talking about paired comparisons in this session so far, I'm going to show you that what we do is in every single meeting of a department, we have an agenda. So you just set the agenda appropriately, and what happens is Fred will be the winner. Here I have Deanna versus Elaine, and everybody prefers Deanna to Elaine. That's unanimous. Deanna versus Connie. Everyone prefers Connie. That's unanimous. Connie versus Barb. Well, that's a little bit more difficult. Nah, 2/3 of the people prefer Barb. Notice the size of the vote. Barb versus Ann. Well, okay, 2/3 of the people really prefer Ann to Barb, so Ann wins. And now Ann versus Fred, 2/3 of the people prefer Fred. And so Fred is the winner. And so who could ever argue with that outcome? Can you do this? Oh, yes, you can. When I was at Northwestern University, never have I done that at UCI. But when I was at Northwestern University, what I did actually was showing some people this right here, and they says, whoa, can that be done? I said, yeah, I'm going to do it tomorrow at a departmental meeting. I said, I'm going to be putting forth such and such. He said, oh, you know, most people don't want that done. And I said, no, I'll get it. And I showed him exactly how I'm going to do it. And then what happens is when I walked out of the meeting, everybody knew what I was going to do, and I did it. And what happened, and I walked out of the meeting, all of a sudden someone looked at me and says, you can fill in that word. He says, you did. Okay. And it really isn't that hard at all. But what I want to do now, and the purpose of this right here, is to show you the source of all possible paired comparison difficulties, all of them. One of them is the ranking. It's called what I call a ranking wheel. I got 6 alternatives here. So I'm going to put 6 numbers. If I had 15, I put 15 numbers here, evenly spaced right around here. You want 20? Put 20 numbers. I couldn't get that in there. Okay. Then I put down the names of the candidates in any way you want, right here. A, B, C, D, E, F. You could put B, A, C. I don't care what you do. And take a look at the ranking. Well, the ranking wheel says that A is ranked 1, B is 2, C is 3, D is 4, E 5, F. So I get this ranking right here. Now what I'm going to do is I'm going to twist by 60 degrees. Now B is in first place, C is in second, D is in third, etc. And I'm going to continue this for 6 times until everyone is in first place precisely once. This ranking coming from this ranking wheel, is the source of all possible. We have known since for a couple hundred years that you could use this to create some examples. The theorem is all possible examples with paired comparison difficulties have this embedded in it somewhere. And so, in fact, what happens here is no candidate is favored in this example because A is in first one time, first place, second place, third place, B. Each candidate's in the same place the same number of times. And so what happens, though, is that the paired comparisons give you cycles. Let's take a look. And again, the reason is lost information. Everything is lost information on here. What we have here is, let's take a look at B and C. B is ahead of C here, B is ahead of C here. Right here C is ahead of B, but then C is going to drop down and B will be ahead of C again. So B will beat C by 5-1. C will beat D by 5-1, all the way around. And really, this is called a Z6 orbit in mathematical terms. And the fact is this is the source of all paired comparison cycles from law, from statistics, engineering, etc. And as I stated, it is an if and only if statement that if you have a cycle, that's embedded in there somewhere. In fact, its statement is that it happens everywhere. Let me give you an example. If you look at it in terms of a coordinate system in profile space, where I have the profiles of a certain distance. So,
what's the rule, Jim? Are we just taking arbitrary binary relations here?
No, I don't care what you use.
Majority rule.
If you want majority rule, if you want to have a cycle which is done by a 60% rule, okay. Super profile, if you want to have a cycle that's caused by Sen's theorem, if you want to have a cycle that's caused by, and I'll give you a couple of examples. They're all here. And what happens is the space of possible profiles is divided into the cycle direction and into the what I call strongly transitive direction, where nothing goes wrong.
But what's missing here, just as a question, is the name of the person. All of your examples have symmetry in the arguments, namely, if the top 10 are switched with the bottom 10, they just change the name of the people.
That's right.
It doesn't change. So these are all examples where we have symmetry in the arguments. Okay.
Yeah, what happens is that the symmetry is in all of these situations in engineering and everything else, whether we believe this. Yeah. And really what happens here also, Charlie, is that, so he's talking about A, B, C. Now I go and put a different ranking here. I can have B, A, C, D, F, E. I can have all of those type situations you want. Whatever situation you want, and I'll get another one.
But in particular, what you don't have is a veto player.
Oh, you still get that if you have a veto player, that if you have a cycle with a veto player, if you can get a cycle with a veto player, if you have a couple of veto players type thing and things, it'll be due to this.
We'll have to talk about that.
Yeah, but if you ever see a cycle with paired comparisons, I don't care what it is, it's due to this. Okay?
Now,
if you are talking about manipulation, you know, we were talking yesterday, and Linda said yesterday in terms of the fact that you don't see many cycles. The source of what causes the cycles are everywhere. If you ever see that you can manipulate with agenda manipulation, if you ever see where you can, some of your manipulations, agenda manipulations, some of the difficulties that you have, it really is due to something like that. And so and these things right here have higher dimensionality than the good stuff.
Okay, so I still have another question.
Good.
You know, we're starting this out, when you decompose it, you're decomposing it into pairs. Let's suppose I decompose it some other way. I decompose 3, 2, 9. So basically my decentralization is not deconstructed into pairs, but deconstructed into arbitrary sets. I'm pretty sure you'd want to partition it, but does this kind of, can you handle that okay?
Yeah, okay. Not with this, I have to use a different symmetry, but yeah. And in fact, my theorem, in terms of the reductionist philosophy, says I don't care what you divide the parts into.
It's got to be a partition, though.
Yep.
The idea of a partition is essential.
Got it. Total. Just a partitioning.
Yeah.
That's it. Now it's the source of all possible pair comparisons. And let's take a look. We've all seen this. We've seen this for the last, almost every lecture in the last 2 days. And this is really coming from the ranking wheel, isn't it? It's when I just write down 1, 2, 3, and I'm rotating the wheel around. And here are the rankings when I put them in terms of pairs. And you see what happens here. If we're going to use majority vote, this will be 2 to 1. A is better than B 2 to 1, B is better than C 2 to 1, and C is better than A 2 to 1. All right. I want to know a little bit more about the lost information. Now, what are the preferences? If you just came in here, saw those parts, what would be the preferences of the individuals? Well, in other words, you're the tallying machine. What are the preferences of the people? Well, they could be A, B, B, C, C, A, right across here, which would give you this. Or they could be this right here, couldn't they? There's no way the machine, the tallying machine, could distinguish between a person's preferences going this way or going this way. That this is the first person's preferences. A is better than B, B is better than C, C is better than A. That the person has cyclic preferences. The person has B better than A, C better than A, C, C, B, B, A, cyclic, etc. And in fact, if you look at it, it turns out there are precisely 5, from those parts, there's precisely 5 different profiles you can have. 4 of them have cycles. 1 of them is transitive. Think of that poor machine. That poor machine is getting all of this input on there, and it doesn't know what are the preferences of the individuals. And so it says, well, let's see, there's 5 possibilities, and 4 of them, 80% of them, say that the right answer is cycle. So I'll ignore that outlier, which is the one that you wanted, the transitive preferences. You know, we've been talking in terms of group versus individual. Well, see, an individual has that extra connecting information in their head. Remember I was talking about the silo effect? You don't have that silo effect when you're looking at the rankings. You can make those connections. You know this is your preferences. The pairwise ranking does not. It says that this is equally likely. And so what you have, it's that the poor machine is trying to do its best, giving what is statistically, probabilistically what is the right answer, and gets it wrong. And so what's lost information? The connecting information. The connecting information, the information that connects the parts. Transitivity, that's what's lost. And when we talk in terms of my more general theorem, what is lost is the connecting information in all of those cases, which then made, once I saw that, it wasn't that hard to prove the theorem. Okay, and there's my comment, individuals versus group. Now, here's an example. Wheaton College used to be an all-women's college. So they were going to get a new president, and they needed to elect a faculty committee to join in on selecting the new committee. Everybody on the faculty knew they wanted to have some women on that committee. A friend of mine, Tommy Ratliff, got a hold of all of the ballots years later, but they kept them and he had them. What happens is the way they went is the following. They had 3 divisions. They had the division of, I don't know, social sciences, maybe humanities, and maybe physical sciences. Each division had 2 candidates. They selected 2 candidates. Each division had a man and a woman as a candidate. Each and every ballot voted, everyone voted for at least 1 woman. And you know what the outcome is going to be. Only men got elected. And what was the reason? Well, we put it into a situation like this where what happens is transitivity was connected with the statement of mixed gender. And we showed all you had here was a cycle, that's all. And that's why you get all men inside there. So can we get cycles? Yeah, if you know where to look for them, they're all around. But really the connection is that we have this separation, this division. The intent of the people was there, but not with when we do it issue by issue type thing, which gets me into my next statement, the discursive dilemma, issue by issue voting, which we talked about a bit yesterday. I think you raised it, Max, didn't you? And so let's suppose we're going to decide the fate of a poor graduate student. Okay, and whether or not he's going to get continued funding. All right, and what we have to do is he has to excel on teaching and research. And the first person that evaluates him says, yeah, he does great on teaching, he does great on research, yeah, continued funding. Next person says, oh, his teaching stinks. Otherwise, and so therefore the answer is no. And the third person says, no, his teaching's okay, his research stinks. So you get no. And so what you do then is, if you look at the outcome, I'm sorry, but, but 2 out of 3 said no, and you don't get funding next year. Okay. But look at what happens if we did it issue by issue. Yes and yes. Okay? If we did issue by issue, we would have the correct answer. Not correct for you. All right? So what we can get is different answers here. But let's take a look. Yes, no is a paired comparison, isn't it? It's yes or no. It's a paired comparison. And I said that all possible paired comparisons come from something like this, including the discursive paradox, etc. Where? Well, what happens is, this means that we're losing intended connections. That's what goes wrong here, which we already know. But take a look. Here's yes, here's AB. Yes, yes, AB, AB. So it's just a name change. Here is no. Here is no. I have no, yes, yes. I got no, different, different. And what happens is here I have no, CA, 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 no, no, yes. It's exactly the same. It's precisely the same as what we had with the Condorcet triplet and with the other thing here. So paired discursion, a discursive dilemma, or issue by issue versus the total concern, are special cases of this whole thing, of the ranking wheel and of this whole phenomenon. Let's take a look at one that's come up quite a bit today. Minimal liberalism. Let me remind you what it says, and then what we can do is find out what it really means. Minimal liberalism, really it's just a special case of Arrow. It's just a special case of Arrow's theorem. Because Arrow says it doesn't matter how you have the AB ranking, how you have the BC ranking, how you have the AC ranking. And all Sen does is gives a special case for it. The minimal liberalism is that each of the 2 of the agents are given a pair, and they can make the decision about what's happening with that pair. Each person can make the decision about what's happening with that pair. So you got AB, you can decide he has CA, AC, can make the decision. And any other pairs, if you have unanimity, that'll be the outcome. The Pareto condition. Well, that's paired comparisons, isn't it? That's a paired comparison because each person is making a decision over an assigned pair, and then we're talking about unanimity on some other pair. And so let's take a look and see what happens. Anne is decisive over AB, and her ranking is ABC. Bob has BCA, and he's decisive over AC. And let's take a look and see what's going to happen here. What happens is Anne chooses AB, BC is unanimity, and CA is because Bob is decisive. And so we have that ranking, which is, again, just a special case of Arrow's theorem. We're just saying for each pair, how are we going to make the decision? Question?
So rather than individual compare these alternatives pairwise, we have just we have 2 people who have assigned.
That's right. Yeah. And Arrow's theorem allows that. He just said, remember, I said, I don't care how you make the decision on A, B, B, C, A, C. You know, we normally think of it as voting. But it has nothing to do with voting. Arrow didn't say anything about voting. He just says, you can find any way you want to get the ranking. Any way you want to have a ranking. So Sen just gives you one special case. But let me now show you that this is not, as we've heard today and yesterday, this is not a statement about individual rights. Number one, it's a statement about lost information, but I'm going to show you what it also means. It's more about a dysfunctional group. Let me show you what I mean by that. Anne is decisive over AB. By being decisive over AB, it's not an innocuous decision. She's creating a strong negative externality for Bob. Because Bob prefers B over A. And strong, because there's someone separating them. And Bob decides between AC, choosing CA, which creates a strong negative externality for Anne.
Incidentally, that's exactly the reason I asked if it was a property rights problem.
Yeah.
Because you have this externality in there.
That's right.
And they said, wait a minute, you're hurting me.
That's
in this indirect way.
And your insight was absolutely correct on there, because what happens is the following. The theorem is that we now know how to find construct all possible Sen paradoxes. And the theorem is that whenever there is a Sen paradox, each agent is going to suffer a strong negative externality. Each agent was going to suffer a strong negative externality, whether or not they're decisive. And the reason is that, quite simple, is that if we have a Sen cycle, some person is not going to have, if you have transitive preferences, you're not going to fit that cycle. One of your ranking is going to be out there, and it's going to be a strong negative externality. There's got to be someone in between. So what you can do is show that. So if you're taking this over into the law type thing, then really what Sen says is it's not that, it's got a dysfunctionality that looks like really Anne is, maybe we shouldn't have her do these things. No, the question is when Anne does it, she hurts somebody else and hurts them seriously. And that's what's happening there. Now, what happens is, and we talked about the prisoner dilemma this morning. You raised it. The prisoner dilemma is a special case of Sen paradox. The reason is the following. In the prisoner dilemma, you could decide right row, left row, and someone in top column, bottom column. You have what? You are able to make the decision over an assigned pair. Top, bottom, right, left. And you just write down the preferences a person has, and you see immediately you have a Sen paradox. And so the Sen paradox is a special case. But I want to show you one thing before I forget. ABC, BCA, look familiar? Theorem. If you got rid of all characteristics of this ranking wheel stuff I said, you will never have a Sen paradox. You will not have a Sen paradox. That the Sen paradox is, for a larger number of candidates or anything, is due to that ranking wheel phenomena that I talked about. It's totally. Take a look, though. Strong negative externality. How do we handle the prisoner's dilemma, which gives you a strong negative externality? Cooperate, you should be here, but you go down to the Nash point and everyone hurt. We use tit for tat as one of the ways to get cooperation. Now, not all Sen paradoxes have the structure of the prisoner's dilemma, but all of them have a strong negative externality, which means that the tit for tat approach works to try to get cooperation with the Sen theorem. It always will work under certain discount rates, the usual type statement. And so that's what you'll get there. Now, where else will this crop up? Well, let's take a look at fishing rights, etc. we have a prisoner's dilemma there, don't we? Yeah, if I'm going to overfish, etc. And so what happens then is, how does society handle that when they can? They punish you. You go out there with your fish and overfish, we're going to blow your damn boat up or something else. Or you'll be ostracized or something else. That's a tit-for-tat type strategy. And so one of the ways in which society handles the send type things, because it's incurring expenses to other people when it does, is really through a de facto tit-for-tat type analysis. Now, and indeed I'm calling attention to the fact that indeed that if you don't have this structure from the ranking wheel, you just plain will not have a send paradox. So now, dimensionality. Yeah, it'll work out fine. Dimensionality. You know, we've been talking about dimensionality as though it's bad, but dimensionality can unleash problems. Why can it unleash problems? It takes at least 2 dimensions to get that ranking wheel. And if you have a ranking wheel with 4 candidates, it takes 3 dimensions. And so in other words, you can prove this mathematically, that you just need more and more issues to get a larger and larger, ranking wheel. And so the role of dimensionality is that it permits you to come up with these ranking wheel type phenomena, which will then cause all possible problems. Now, but remember, dimensionality can unleash problems, but it need not. We've been talking about it as though once we have 2 dimensions or 3 dimensions or something like that, or 3 issues, that we're going to have a cycle. No, you're not going to necessarily have a cycle. You have to have more. What you need to do is have a certain kind of a conflict to be able to get this, where separability causes problems. That's what you need. And here's the one that I had down that really is essentially what Leo had already said. I'm going to write the great American novel. You don't realize that, but I am. But to do that, I need a better computer than this right here. So I go borrow about $3,000 from Linda. Linda says, sure, Don. But she says, you go bankrupt, I get the computer. That's fine. Then what I do is I'm working along and, you know, nothing's coming. So I go over to Leo. Hey, Leo, how about 3,000? Leo says, sure, but Leo, he's a law professor. So he knows he has to register, and poor Linda, she's like an economist. And didn't realize you have to. And she's been listening to it. You don't have to listen to the laws anyway. And so what Leo does is register it. Now here's the catch. If he registers it, he has first priority if I go bankrupt. But the point is, and here is where the dimensionality sneaks up. If indeed he does not, I mean, if he knew about Linda, Linda still has priority over him. Sounds innocuous, but you don't have an extension of that first one, that if I go bankrupt, the money goes to. It's not a linear extension of it. It is a new direction. And so the dimensions crop up so easily and so innocuously. And so then what happens is Max, thank you, I borrowed money from Max. Max right here, he doesn't know about those 2. He loans me the money, he registers it. Of course, I'm going to go bankrupt. And what happens if we take a look at this according to the rules? Linda dominates Leo's interests, right? She registered before, I mean, she had it, she didn't register, but she had it before and Leo knew about it. Leo dominates Max. You registered second, he registered first. And of course, Max not knowing anything about Linda, he dominates Linda. And you have your cycle. We've already discussed that with Leo's presentation, but in various different ways. But the point of this right here is the following. It's that dimensionality can crop up incredibly in very innocuous type settings. You just don't even realize you're getting another dimension thrown in. And once you get 2 dimensions, what is it that you're doing? Is you're unleashing, or you're creating the possibility now of getting that ranking wheel, that putting that wheel in there and spinning the thing. And geometrically, which means you're going to have the difficulties. And so really, what's the message? As the number of issues increases, so do the problems. And not only that, but the likelihood of problems keeps cropping up. But the problems all involve lost information, and I've identified that if you're looking at paired comparisons, if you want to do like Charlie asked, if you want to make other partitions, sure, I know how to do it. I'll show you how to get what are the problems there. And you get difficulties there. And what happens then is you just need to know what information is lost, because if we know what information is lost, then the next step is to try to get resolutions, isn't it? Is to try to find ways of putting that information up or getting rid of the lost information, showing it doesn't, ways to show that we can get rid around that. But I want to, really the message is break free from the arrow-send paradigm. The arrow-send paradigm are important, but the problems are more interesting elsewhere. You know the theorem that I proved about the reductionist philosophy? Nowhere in there was the word transitivity. It has nothing to do with transitivity. In place of transitivity is a condition, is a constraint. In place of that, I put Newton's equations or something else. And so if you break the constraint of the arrow-send paradigm and those right there and say, really what the problem is the reductionist philosophy, which we use everywhere. And if you're looking at it from the perspective of, that what's happening is connections are lost, and that's when there's conflict, that's what's going to cause difficulties. Once you have that, then there's much more. And I guess that's it. So with that, I thank you. Yeah.
One of my favorite series of books is Robert Caro's biography of LBJ, and one of the middle ones is called Master of the Senate, which isn't hyperbole because LBJ was probably the most effective majority leader in the Senate's ever known. But when I think back to how he got so much legislation through, an awful lot of it follows this model of pairwise comparison for an individual senator between, well, I know you don't like this issue much, but what about this issue? And he would just listen to senators and listen and listen and listen, and sort of on a pairwise basis say, well, yeah, I hate this, but I really hate this more. And so he'd structure the whole thing so that each senator was still hanging on to their preference, and yet the vote came out his way. It's really, it would be interesting to go back and rework some of the legislative maneuvers he did there.
Paul Simon retired from the U.S. Senate in 1992. Big issue in 1992 was balanced budget. Paul Simon put forth a balanced budget amendment before he retired to go to the Senate. Nobody in the Senate really wanted to have the balanced budget amendment. Nobody in the Senate wanted to vote against it. Why? Political suicide. So what did they do? And it was actually in the paper, and I've got the news item somewhere in my big trash stuff that I call an office. And what happens in there is was the senator from Oklahoma introduced a new, better balanced budget amendment, and stated precisely what he was trying to do. He's trying to create a cycle. So therefore, the first vote was between the two balanced budget amendments. Everyone could say they voted for one or the other. And then the winning one was up against the status quo and lost, didn't get the right number of votes. And so indeed, the politicians are well aware of these type of difficulties. These types of opportunities. Very much aware of it. Yeah.
So you say it's about information loss at sort of the
connecting information.
Level,
yeah.
Connecting information that you see, for example, under transitivity, but maybe more generally under the reductionist enterprise. But so just taking the transitivity as an example, recognizing your more general point, I'm wondering if it's actually has to be information loss there, or just a tension between the following two ideas. I mean, when we do transitivity, right, we are committed to the following set of idea, that having seen A and B together and chosen A, and having seen B and C together and having chosen B, we are already committed in this more holistic way, without seeing A and C, that A will be chosen over C, right? That's what transitivity tells us. So transitivity, in some sense, ignores the information that we might get when we actually look at A and C together.
That's
right?
correct.
So there's a sense in which the information loss can be interpreted the other way, right?
Yeah.
So it's not that the reduction fails to see the holistic information.
Oh, but it
that
does.
The whole is kind of indifferent to the reductive information, isn't it? So it's just where the information is, right?
Yeah, you're partially correct there. What happens is, as we were saying before, in terms of what Leo and entering the talk there, and all of us were discussing, maybe cycles aren't always that bad or things like that. Well, I'm not really worried about cycles. My job is to try to understand why they crop up. So if they're bad, I know why they crop up, and also how do we get around them. And so what we have is a large number of situations, like I had with the I'll elect Fred. I have seen departments where I was on the governing board for the one of the astronomy type groups because of my interest when I wear my astronomy hat. And they had an outcome where they said, well, gee, it was a cycle there, but they never thought of looking for the last C versus A. They had A greater than B and B greater than C, and they said it just doesn't seem right to us. And they never bothered to check for A and C. If they had, they would have said, gee, we want something else. Let's find another voting procedure. So one of the troubles is that we try to impart our sense of transitivity on societal outcomes. With us, we make the connections. We know that if I have A, B, and B, C, that A is greater than C type thing, unless you're Tversky and Kahneman. But what happens is that we know that that's going to happen. The voting rule doesn't have that advantage, and yet we try to have it inside there. And it severs these connections. And so if you want to have some sort of, if you do find cycles causing difficulties or something like that, there has to be a way of connecting the parts when the parts are being analyzed. That's the only way. The reductionist result that I have says that's the only way you're going to be able to get it. The only way.
But it seems to me it's a more general problem in many ways than your sort of analysis suggests, it seems to me, because even your very general analysis. So in the version of the way that Charlie did it yesterday on contraction consistency, right? Rays overlapping circles, right? So there had to be, under that idea, a kind of consistency in our choice between X and Y, if X and Y continue to be available, right, in the next set.
Oh, you mean in his examples that he created? Yeah.
Well, he had I think he was just trying to give us the property of a kind of choice consistency condition, right? And so that idea of choice consistency as we add or subtract alternatives where the two previously ranked alternatives are still available is a way of ignoring, right, even though it's actually a paradigmatic choice consistency condition that rational choice theorists are committed to, is a way of ignoring the fact that the whole has changed, actually, right? The set is different in virtue of the fact that additional alternatives have been added or some subtracted, even though the same pair continues to exist for us, right? So that's a version of this problem. It has nothing to do with pairs as such.
No.
It has just smaller sets. And it's nothing to do with transitivity, of course.
You mean rationality mandates the losing of certain information?
Well, it's an
information.
invariance. I mean, all of these things are invariance conditions on changes, right? Which is to say that's what consistency is, right? I mean, it's an invariance condition on changing information about other alternatives, right? So I don't know what it would be not to have something of this going on, right? I mean, we can't be. The argument would be to be entirely holistic about this. Would in some sense miss the possibility of being consistent in these quite elements.
No. For example, I can use paired comparisons. And I know how now to put them together so that I will get a result that is much better than the plurality or anything else. What you have to do is see the connections among the different parts. For example, suppose I have that the AB A is better than B by, say, 60 to 40. And I have that B is better than C by, oh, I don't know, let's say 55 to 45. And what do you want for, do you want A, C, or C? I don't care which one. Which do you want?
What is my final choice?
Yeah, do you want, for the example I'm going to write down, do you want A better than C or C better than A?
Oh, let's be perverse. Let's do
C. All right, and so what tally do you want to put down there? What tally? 100 voters.
70-30.
70-30, okay. And so the question that we want to know now, it's that we know what causes the cycles. What causes the cycle is that ranking wheel that I showed you. And so the question is how do I extract that from the data? Because there should be a tie, as I showed you. There's, the argument is, there's an argument that that should be a tie. So how do we extract that? And a simple way to extract that from the data is to do the following. A's tally is going to be 60 plus 30. This plus this. You know what A gets in those two elections. B's tally is going to be 40 plus 55. And C's tally is going to be 70 plus 45, 115. And so the ranking is going to be CBA. And what you can do is you can prove that if you take, I don't care where the problem came from, what are the individual preferences or anything else, that if you do this approach right here, and you go through this right here, that you are extracting that cycle out of there. You're extracting all cycles out of there, and all the information you have left is very nice and transitive. So the statement is, and I'm not going to go through the proof of that, I will later if you want privately, but the statement is, no, I'll go through the proof. What happens is, here I have A, B, C, B, C, A, C, A, B. Let's take a look at A. A beats B by 2 to 1. B beats C by 2 to 1, and C beats A by 2 to 1. A gets 2 plus 1 is 3 points. B gets 2 plus 1 is 3 points, and C gets 2 plus 1 is 3 points. And so the cycles all cancel out. And that works for any number of candidates. And the cycles all cancel out. And so there's a way now of extracting the cyclic type of the data in there that should be a tie, but created the cycle, and to reunite all of the information. By knowing what causes the cycle, we now can go back and find methods that everything will work. And this is a method I've been proposing to engineers, for example, because they look at paired comparisons. They can't look at it holistically, it's too darn expensive. But they want to be able to get an answer. And so this is one of the approaches which I proposed.
So, John, could I ask you to clarify just what you mean by this ranking wheel generates all pairwise comparison problems? So, for example, you can generate all the different rankings through the ranking wheel. You can have these rows. You can change the order of the rows.
Yeah, sure. It doesn't matter. Yeah.
But if you take within any given row and you take A, for example, and replace it with B, swap them around.
All the way through? Same thing.
But in any one row, just
yeah, sure. So
then you don't get a problem.
Oh yeah, you still do. Because really what happens is, what you're doing is you had a profile which was in a cyclic direction. Yes. And what you're doing is, in looking at it from, you're now getting a profile that has a big cycle, but a little bit of a transitive. So you still will. So that theorem's a little bit, a little nebulous. What happens is that what I did is it's just like the Cartesian coordinates. It's like X direction, everything is fine. Y direction, everything's bad. I can have a vector that has components in both directions. And what you're doing is you're giving me an example of a component in both directions. But if there's any difficulties, then some of that's inside there. So by knowing what causes the problem, and the same thing, Charlie, if we look at other partitions, by knowing what causes the problems, we now have a means of going back and analyzing how we get around it. That's why we use the board account. This is the board account. Sorry. Yes, John.
Yeah, I have a couple questions. Two, I'll tell you both of them first. first.
Okay.
One is you're using these binary structures.
Yeah.
If we look at things like majority rule, of course, it's filled with cycles. There's cycles in types of cycles.
Yeah.
And overlapping cycles. And my intuition is not clear. My intuition is not clear about what would happen if we use this kind of aggregated method you're using here, when we have cycles on top of cycles and things like that.
Special case.
Doesn't change. So if I have
Doesn't change.
If I have one big cycle and they have lots of little cycles, then I just have to look at the numerical structure to see what.
That's right. And look here, I have A, B, C, D, E.
Yeah, that's good.
Here, A is better than B, B is better than C, C is better than D, D. And this is what you get from the ranking wheel, and then you get this right here. You get these cycles.
Yeah, just put another little cycle.
Yeah, yeah. And they're all special cases of exactly the same phenomenon.
But will your numerical thing rank one cycle above another cycle?
You can get it to do so, yes.
That's what I was thinking. Okay.
You can do,
That's my first question.
and in fact, what happens is there's an unsolved problem which now is solved, and that is to find precisely all possible paired comparison outcomes, tallies you can get, and it's done precisely in the way you're talking about.
Okay, so now I have another question.
Oh, you don't know about that.
Part of the story you were telling here was, there's a missing dimension or missing piece of information. So let's take an example. It's kind of like a legal example. So we have a guy who is walking along the street. He sees an apple, and he has the right to pick up that apple and eat it. Now, the person's apple it was this person who put him out in the stand. Okay, he has no rights to prevent this guy from taking it. So the question is, do you put your apple on the stand? The answer is no, because you know he's going to come along and take the apple without paying for it.
I'm that kind of guy.
So it's a prisoner's dilemma. We're not going to get the apples. Now let's make a slight change. Let's put a legal system in there which says that if, as a matter of fact, if you take his apple, he has recourse on you to collect the money. All right, now we've saved the problem that we've taken this prisoner's dilemma due to a bad property rights and incorporated the externality in essence so that the system works well. The question is, now, did I add a bit of information?
Yeah.
What is it I added?
The-
Did I add an object, namely another option? He took the apple and he paid me and, etc. So I have another brand new event. Is that the kind of thing that you need in order to eliminate this merger from prisoner's dilemma back into social choice?
Yes, and but the way this has to be done, it's that you see, what Charlie's doing is saying, you got the situation, let's throw something else on it.
I'm changing the game.
You're changing the game. And no, I approve of that. Changing the game so that what we do is we have now a connection between the different parts. And as I stated with the theorem there, you need to create connections of that type. But some connections are useless and some connections are useful. And the question is which ones are useful? And they're going to be the ones that handle that ranking wheel. That's where the thing comes. If they don't handle the ranking wheel, they're useless.
Let me push that just a little bit further.
You're introducing into the second mover's decision information about the first person's welfare.
Yeah. And you're taking into account those.
I can see where you can make that argument. I can see that. But I have another, let me push it just a little bit.
Okay.
Okay, take a regular old prisoner's dilemma. Now notice that we end up in the dilemma. It's non-pro-optimal outcome. Notice that no one has an interest in changing this preference given the decision of the other. Right? That's a structure. So in some sense, the game is well defined. The Nash equilibrium is well defined. There's no externality in the sense of the sin example, which is not so exciting. What do you have to add then to get? You're saying, I think you've got to say that this is not a problem. Right? This is not a cycle.
This right here?
Now let's see what it is. I was looking for.
So what happens is if we have 4, 4, the top person wants to move to the right. Here, the person wants to move down. And 0, 0 is the, do I have that right?
Well, no, the top guy doesn't want to move down, so the top one does not dominate the bottom one. So you don't have dominance for the principle in this example. because the -2 should, put -2 down and you will.
-2 down where?
On the right, oh, no, on the right. Yeah, right, put -2.
No. Oh, I see. You want -2 here?
Yeah, and then put the -2 0.
Minus,
So those -2, no, the -2 zeros.
here.
Good.
Yeah, okay.
So now this
Yeah,
guy would always prefer to go down, this guy always
Yep.
prefer right, so we end up down
Yeah,
here.
yeah.
So now that's a nice consistent structure of rights. We systematically run here. There's no externality in the sense that given what you're going to do, I'm going to do. So now we have the dominance principle working for us.
Now let me show you where sense
So
theorem
the
comes in
question
here.
is, how do you deal with that in this other kind of philosophy?
Let me show you where sense theorem comes in here. A, B, C, D. From here you can write down both persons' preferences, right? Because one person right here prefers B is preferred to A, is preferred to D, is preferred to C. And this person right here prefers D, is preferred to A, is preferred to B, is preferred to C. Okay? And now, so therefore you got your preferences. Now what does the, who is decisive over AB? Well, the top person is decisive over AB and over DC. The top person can decide whether, if you're right here, whether you're going to have A or B,
Right.
and can decide whether you're going to have D or C.
Yeah.
So this person is the decisive person over the
So basically-
over a pair, over two pairs in this case, and the role player is decisive over two pairs.
Yeah, but then my reply is, the sin example is just completely uninteresting because it doesn't say anything other than we have prisoner's dilemma, and we knew that from economics from the beginning of time.
No. What I'm doing is I'm just showing, because Leo talked and several other people talked about the prisoner's dilemma, and I wanted to show where it fits into sense theorem is what I'm doing here. And now if we're going to talk about externalities, then we have to talk about what are the type of conditions. You have a question?
Yeah.
Rick?
Okay.
Just quickly on this though, I think that's a little unfair to what Sen is trying to do, right? Sen is trying to show that if you assigned rights to people where you thought that that was their prerogative to choose, so for example, in a prisoner's dilemma, so now that there's normative force in the fact that row chooses row 2 and column chooses column 2. And you will recognize that there's normative force there.
Sure.
That might be enough not
Sure.
to worry about the fact they end up in the Pareto principle.
Sure.
That's all he's trying to say, right? That is, so, you know, the person who
I see.
only worries about the Pareto principle thinks the prisoner's dilemma is a problem.
Yeah, but
The person who thinks that it matters that you get to choose. So for example, in his original example, that one party goes to read the book at the library, right, is the wrong person from the point of view of the two people, right? It ends up that Rude reads the book rather than Prude, but both Prude and Rude prefers that Prude reads it. You know, that sort of story. You know, that's just the exercise of the rights in reading the book in the library, right? And so that is a Pareto inferior outcome. The rights theorist simply says, fine. I mean, you know, there is a tension between rights and the Pareto principle. So be it.
Okay, let me answer partially about Pareto. I don't really care about Pareto. Just one is decisive over a pair. Agent 2 is decisive over a pair. You give me whatever rule you want for the other pair. I don't care. You want unanimity? Fine. You want majority rule? Fine. If you want to have flip a coin? Fine. I don't care. You still get the same problem.
Nor does Sen. So Sen says the rights, the exercise of the rights by the two individuals jointly leads to an outcome.
Yeah.
One version of not liking that outcome is that it violates the Pareto principle. As you say, another version might be it violates something else. All he's saying is those people who normatively want to support the rights are going to sometimes show you a violation of these other principles, including Pareto. That's all he's
Yeah.
trying to say.
And what I'm saying is one of the things that he's showing is that if I choose between A and B to get a cycle, I'm creating a strong negative externality for him, and so therefore they're not innocuous rights, no matter what he says.
We exercise rights all the time
Yeah.
that generate externalities. That's
Sure.
what it is to have rights.
Strong negative ones, yeah.
Yeah, I mean, that's what,
Sure.
you may not like what I read, that's what it is to have a right. I mean,
Yeah.
rights are not actually supported in the space of preferences, they're supported in some other space.
That's right.
The space about rights, normative concerns about rights.
I'm
So
not
that they violate preferences, even unanimously held ones, is hardly a surprise.
My point is to show that there are consequences, that there are other interpretations of error of Sen's theorem, and it fits in with the prisoner's dilemma, and that when we tie it in with all of these type of directions, we now have possibilities of finding ways to get around these problems, which we said, gee, we have to give up this or we have to give up that. No, we don't. Just like with the prisoner's dilemma, we don't have to. We know there are ways for tit for tat and other ways of getting cooperation. And it turns out that when you analyze it from this approach, you now have, for any Sen structure, because of the strong negative externalities, you have whatever structure you could use in a prisoner's dilemma with the same constraints, you know, delta has to be greater than something or another. You have exactly the same type of things there. Leo?
Yeah, I want to take issue a little bit with your lost information perspective, which I find very helpful, but like many perspectives, while it helps with some things, I think it blinds us to others. So here's the situation where I think it might blind us to something. So suppose we've got the ranking wheel configuration for 3 choices for A, B, C, and so on, the cyclical configuration. And we're trying to decide which alternative ought to win when we've got these 3 alternatives in that configuration. And since every alternative is ranked 1 by one person, and second by another, and third by another, seems like the fair outcome is some sort of tie, and however we choose to deal with ties, that's what we should do here. Now, one of the alternatives disappears, meaning one of the candidates dies. Now from one perspective, we now have 2 candidates, and the situation is no longer symmetrical. It's become asymmetrical because, you know, now there's a 2/3 majority for one versus the other. But there still is this issue. So do we care about the more symmetrical perspective that we had before when the now dead candidate was part of the picture? Or should we think about it from this more asymmetrical angle, which suggests a more asymmetrical outcome that deletes the candidate? It's not so much a matter of lost information as for whether we ought to or ought to not inject that information.
Sure.
Our feelings about this third candidate into the picture.
Sure.
So it's not, I mean, the dilemma here is not what to, whether to, overlooking information, but making this decision in the first place whether this is information you want to have in there or not at all.
I agree with you. And in fact, it's as though you have to understand what is the lost information, what are the costs. Because if you're going to say that, well, I want to ignore or want to put it back in again, you have to understand what is it that you're losing, or what is it that you would have to put back into the system. Getting late, so I don't want to go into it, but if you were talking in terms of projections, dropping something out, you can see the consequences. Almost any positional rule, plurality, anything you want, I can create an example with A, B, C, D, E. Drop E and everything's going to reverse. And you know where the source comes from? The ranking wheel. I can create in terms of the ranking wheel. Because the ranking wheel, if I have a ranking, I'll just do it with 4, A, B, C, D, B, C, D, A, C, D, A, B, and D, A, B, C. Okay, that should be a tie. It is for the plurality vote. Take a candidate and drop it, D. Now I have A, B, C, and oops, I get a ranking wheel, but then I have an extra ranking, and that's what causes all of these paradoxes. So we can now find all possible paradoxes of dropping candidates and why they crop up on that type. And they're all tied in.
On this primary decision, whether D ought to be included or not.
Yeah, I know. And that is, I'm going to leave to the lawyers and the law professors, because all I'm doing is just saying, hey, you want to know why these problems crop up? They're cropped up because information you thought was being used is not being used. That's what I'm telling you. And I'm telling you what information you thought was being incorporated and not. And I'll leave it up to you to decide whether that's important or not important. I really couldn't care because different situations have different type of answers. My job is to try to tell you what causes these difficulties. Remember the title was the source of all of these paradoxes. It is to tell you what causes these problems. And once you have that information, then you can go to the next step. That's really all I have.
In other words, you're going to avoid the hard problems.
I'm avoiding the hard problems. We'll let those for the law professors. Okay. I think really we should get ready for lunch. I'm there. Okay.